we started talking really about the atom, some of the important, excuse me, some of the important experiments that led to sort of our understanding of the atom. We talked about several sort of experiments. First couple really dealt with the electron, which is our negatively charged subatomic particle. We had our CRT tubes there that Thomson used, and that in sort of combination with Milligan and his oil drop experiment, we were able to really sort of determine the mass of an electron, like 9.09 times 10 to minus 28 grams. So very, very small sort of mass. At that point, it was believed, as we talked about, again, the atom was electrically neutral. So obviously our electrons are negatively charged. So the atom was thought to obviously have some type of positive component. And one of the sort of earliest models of the atom was one sort of put forth by Thomson, which was again sort of a, was referred to as the Plum pudding model. And remember, in that model, basically, he said that it was sort of a sphere of positive charge all spread out over it with our electrons that were embedded inside. And that most of the mass was really made up of these electrons that were sort of embedded in that sort of sphere of positive charge that was spread all out. And this was sort of the accepted model of the atom until really the next sort of big experiment came along that sort of helped us in the understanding of the atom. And that was obviously done by Rutherford. He did, again, as we talked about it towards the end last time, the gold foil experiment. And in the gold foil experiment, what he basically did was he shot alpha particles, which are positively charged radioactive particles, at pieces of gold foil and other metals. And really based on, as we talked about last time, sort of the early model here of the atom, he really believed that, obviously we talked about that things that have the same charge really don't like to be near each other, and things with opposite charges are attracted to each other. So here they really thought that because these alpha particles are positively charged and they're heavy and moving really fast, you know, they would go through, but there would be really some deflection as it went through sort of the atom, again, hitting that positive charge. But again, it's kind of large, it's moving very fast. They'll be able to sort of puncture through it. I think we talked about sort of an example. If you just held a piece of paper up and kind of shoved the pen through it, right, it would go through with some resistance. It's kind of the same idea. And as we sort of talked about at the end there, they were really surprised that for the most part, most of the alpha particles went through pretty much undeflected. And every so often, what they were able to see was, you know, most of them just kind of sailed through, no problem. But every so often, one would bounce off at these really sort of large angles. And that was sort of surprising based on sort of the early model here of the atom. So they had to sort of think about the atom at this point, and really came to the conclusion that perhaps the Plum pudding model here is not so correct. And they had to come up with basically a new model, or sort of the modern version of the atom. And basically what they said was that the atom is mostly empty space. Again, that is what accounts for the guys going through with no problem, the alpha particles. What accounts for those really large sort of angled shots that came out is it had to hit obviously something, as we talked about, that was very, very densely positive. Since the alpha particles are positive, it had to hit something very positive in order for it to basically propel out into these large angles. And they called that basically our nucleus there, nice positive core, which was our nucleus. As later found, that is really where we have our protons, which are positively charged. And also later on, as we'll talk about here in just a second, that's also where our neutrons are, which have no charge. In like 1930 or so, they were sort of discovered as well. The other idea was that we have our electrons really traveling randomly, if you will. Again, electrons don't travel in a nice, pretty circle around the nucleus. They do travel in sort of random patterns. But there, as we talked about as well, some electrons, which obviously are negatively charged, and then nucleus, which is positively charged. And that's really what sort of holds the electrons instead of them all just being able to kind of fly away. There is some attraction to the nucleus, which holds them as they're sort of traveling in these sort of random sort of patterns around it. And the main other difference between the two models is in the modern version here, sort of the correct version, if you will, most of the mass of the atom is the nucleus. So most of the mass of the atom there is actually the nucleus there. And as we'll see here in just a second, it does contain protons, it does contain neutrons, and a proton and a neutron individually are both about 1,800 or so times heavier than any electron that's flying around. So it makes sense that most of the mass of the atom there is made up of that nucleus. Any questions on any of that stuff we talked about last time? So here's just a table of some of the obviously experiments that we talked about here that sort of helped us understand the structure of the atom. We had our CRT experiments, our Millikan oil drop experiments, and then obviously our Rutherford experiment there at the end. And again, just sort of a summary of all that. Again, the first couple we talked about leading to the mass of an electron, and obviously the Rutherford experiment leading us to a better understanding of really what the structure of the atom is. And as we talked about last time, pretty much you do need to be familiar with, all those things, sort of what the experiments were, as we talked about, and sort of what came out of those experiments and how they led to sort of the understanding of obviously the structure of the atom, in addition to obviously the early model there, the plum pudding model, sort of what it looked like, and its sort of differences between the current model, if you will, modern model, and that one. Any questions on sort of what you need to know there? Okay. So we sort of talked about here that our protons are found there in the nucleus, and they are what really accounts for the positive charge that we see in an atom. And it is what really, in a sense, sort of balances out the negative charge from the electrons. And the mass of a proton, as we can see here, is 1.67252 times 10 to the minus 24 grams. That is again about 1,800. Whoops, sorry. That is about 1,840 times heavier than an electron. Again, leading to the understanding, as we just talked about, that the nucleus there is obviously most of the mass of the atom. We'll also see why it goes out to so many digits there in just a second, but it is about 1.67252 times 10 to the minus 24. Remember, our electron there is 909 times 10 to the minus 28 grams. So obviously that is a much smaller number, a lot more zeros right in front of the numbers, making it much, much smaller. Now, at this stage in sort of experiments, it was really believed that the nucleus really comprises most of the mass of the atom, but it actually is really, really small. You could think of it like, the big football stadium is the atom, and then like, the ball there on the 50-yard line is the, kind of like the nucleus, maybe a marble on the 50-yard line there as well. Or if you ever been to the Superdome, anybody been to the Superdome? No. You feel like you're falling out of the seats. They're so tall. The tall seats are like leaning this way. So you get up, you start walking, you're like, whoa, it's gonna fall. But that's good. Anybody go to the Super Bowl yesterday? No? All right. I know you wouldn't be here if you went to the Super Bowl yesterday. I know. All right. So obviously, as we talked about, the protons are confined to the nucleus. And obviously, the electrons are basically spread out in that sort of empty space. They're sometimes called an electron cloud, that sort of space where the electrons are sort of flying around in that area. As we talk about in the next chapter as well, and we touched upon this, we really don't know at any given point in time how those electrons are moving. The best we could really do is sort of like, I have a very good probability that you could find an electron in a particular spot, in the atom. So the neutron was sort of the last subatomic particle that was found, and it really wasn't found until 1932 by James Chadwick. And he basically noticed when he did a lot of experiments that there was a lot of particles coming off like gamma rays or similar to gamma rays. And gamma rays basically are radioactive particles that have no charge. So he found these sort of similar particles sort of coming off in his experiments, and he called them neutrons. And the neutrons there have a mass of 1.67495 times 10 to the minus 24. And it just barely beats out. Slightly heavier than neutron than a proton, hence why they go so many. Subatomic particles, it is actually the neutrons that are the heaviest, followed really closely by the protons, and then it is the electrons, which are the lightest of all three by about 1,800 times, between each of those. Obviously, as we've talked about, the location of these guys are in the nucleus, and obviously the electrons are moving out from the nucleus. Any questions on that there? All right, so obviously it was named neutrons and have no charge. You do need to be familiar with where we find everybody, right? All of these three particles, where they are found in the atom, and obviously their charges. So again, protons are positively charged, electrons negatively charged, and obviously neutrons have no charge. Do you need to know the actual masses of each of those? You don't. They probably will be given to you, maybe. But you do need to know, again, that the neutron is the heaviest of all three, followed by the proton, and again, the electron being the lightest of all three. Any questions on that there? Yeah. This should be chapter 4. Yeah. Other questions? All right, so our modern concept of the structure of the atom, here's a much prettier picture. Again, this is our nucleus here, which is really small. That is our positive charge, and most of the mass of the atom found there. This is what is sometimes referred to as the electron density map. And it's really the empty space within the atom where our electrons are flying around. And when you look at it, I guess you can kind of see it on the screen there. The darker shade, if you will, of red here indicates a higher probability of finding electrons. And as it sort of moves out, you can see it gets lighter and lighter. And that means there's a less of a probability of finding electrons in that part of the atom. Just looking at this map, we see that there's a very high probability of finding electrons near what? Yeah, near the nucleus, right? It's really the darkest color near the nucleus. Again, doesn't mean that they're traveling in pretty circles, just that there's a pretty good chance that you would find that. Again, because opposites attract. So the positive and negative guys are attracted to one another. And obviously, as you move out to the outside, you're getting less and less of it. Also, those electrons are not going to be held as tightly the further away it gets from the nucleus, as opposed to those guys that are closer to. All right. Any questions on the atom, the structure of the atom? Anything? Yeah. Say again. I don't know if you can say they have most random motions. They're all pretty much moving pretty randomly, and we really don't know exactly, how they're moving or, where they're moving. There's what's known as the Heisenberg uncertainty principle, which basically says if you know more about how they're moving, you know less about their location, and vice versa. If you know more about where their location is, you know less and less sort of how they're traveling. So there's really no good way to know, the guys on the outside are sort of moving in a more random motion. What we do know is the ones on the outside are not being held as tightly because they're further away from that positive charge nucleus. And that's why, as we'll talk about in later chapters, those are really the ones that are involved in bonding, because they're out there, they're far away from the nucleus, they're not held as tightly, they're able to interact with other electrons and really participate in bonding and stuff like that. Other questions? Okay. So the good news is the chemistry really of atoms does come from electrons. And as I just mentioned, that's pretty much what happens. It's all about bonding. When we talk about regular chemical reactions, talk about nuclear reactions, that's different. That's neutrons and protons. Really, everything we talk about in pretty much all chemical reactions is really about electrons. And as I mentioned before, if you think about kind of a very bad drawing here, two atoms coming together, we have these electrons on the outside, so they're clearly the first ones that are going to come in contact with each other as those atoms sort of come together, and they're really the ones that help us break bonds, make bonds, and are a result of all those chemical reactions that we see. So let's talk a little bit about some really important properties of atoms, and that is the atomic number, the mass number, and isotopes. So we'll start with atomic number. Now, the atomic number is sometimes abbreviated with a Z. And the definition of the atomic number is the number of protons that you find in an atom. And where can we find the atomic number? We can find the atomic number on the periodic table. And if you look at the periodic table, it is all the numbers that come above the symbol. So a lot of times right above the symbol, in this case, above to the right, those are all the atomic numbers for each of the elements. And when you look at the atomic numbers that are up there, you should notice something. Do any of the numbers repeat in terms of the numbers that are on top? The answer is no. So every single element has its own atomic number, which means if you ever need to know the atomic number of carbon there, you can look at the periodic table and it would be 6. And what that tells you is that has 6 protons, which protons are positively charged. And if we had a neutral carbon atom, it would have to have the same number of negatively charged guys, right? Which are our electrons, which means if we had a neutral carbon atom, it should have 6 protons, which are positive, and to balance it out, it should also have 6 electrons, which are negative in that particular case. It is important to remember, though, that if you are asked what is the definition of atomic number, it is just the protons. It is not protons and electrons, which is a common wrong answer. It just so happens that if you're dealing with something that is neutral, which means it has no charge, it has to have an equal number of electrons, obviously, there. Again, we can look at nitrogen. When you look at nitrogen, again, you see the 7, and that means that a neutral nitrogen atom should have 7 protons and also should have 7 electrons. Any questions about there? Now, the mass number is another really important sort of number, if you will, that we look or calculate sometimes. And what is the mass number? The mass number is sometimes abbreviated with an A. It is the number of protons and neutrons that you find in the atom of an element. So mass number is protons and neutrons. And if we think about that, the mass number, protons plus neutrons, the atomic number is protons, which means if I subtract those two, that would allow me to figure out the number of neutrons. So if you take the mass number and you subtract it from the atomic number, it will tell you how many neutrons there are in a particular atom. Except for everybody, except for hydrogen, I should say, is a better way to put that. Except for hydrogen, every single element has protons, electrons, and neutrons. Hydrogen does not. Hydrogen has a proton and it has an electron. It does not have a neutron, but every single other element there will have all 3, except for hydrogen, which is why it has some special properties. And years ago on some periodic tables, including ones I think that used to hang here, you would sometimes see hydrogen over here, and you would sometimes see like hydrogen over here as well on both sides of the periodic table. Not too many made these days, still put hydrogen sort of to the right, but you used to see it basically on both sides for some reasons. But hydrogen does have some special properties, and one of those is it doesn't have neutrons. Now, when you're asked to calculate or give the atomic number, give the mass number, if you're asked how many protons, electrons, or neutrons there are, all those should be positive whole numbers. So they all should be positive whole numbers. So the question is, when we go to our periodic table and we look at it, is the mass number found on the periodic table? The answer is actually no, it is not. So if you look at all of the bottom numbers on the periodic table, they're pretty much all decimals, right? They're not whole numbers. And atomic number, mass number, protons, electrons, and neutrons need to be whole numbers. Can't have like a half of an electron kind of flying around. So although most people like to use that number there on the periodic table as the mass number, it actually is not the mass number. It is what we'll talk about in another chapter. It is what is known as the atomic mass, which is different than the mass number. So only the atomic number can be found on the periodic table. Protons, electrons, neutrons, mass number, you'll be given enough information to calculate those things, but it is not the number that you find on the periodic table. Do not be the person that writes a number from the periodic table on the exam, not this exam, next exam, for the mass number. What sometimes does confuse people is if you sometimes calculate the mass number, it is a number very, very close to the number that you see on the periodic table. It says they're all based on protons, electrons, and neutrons, and that's what sometimes confuses people. But just keep in mind, only atomic number can be found there on the periodic table. By the way, out of protons, electrons, and neutrons, which one is the most important one in terms of what element we're dealing with? It is the protons, yeah? The protons are the atomic number. Determines what element you're talking with. As we talked about a second ago, if I have carbon that has atomic number 6, I will never find like a boron with an atomic number of 6 because that's carbon. Boron will always have an atomic number of 5. So again, it is the protons that determine what element you're dealing with. And in normal chemical reactions, it's only the electrons that change, which is why we have conservation of the elements. We don't lose elements along the way. It is when we deal with nuclear reactions, the neutrons, the protons change, which actually does change the elements, which we don't deal with in this class. But in chemical reactions, because it only really deals with the electrons, the protons and stuff in the nucleus are not touched, then we have that conservation of elements, which is why when we balance the equation and we got 6 carbons on the left, we got to end up with 6 on the right because we're not changing elements because no protons or any of those things are being touched. Any questions on that? Now, what are isotopes? Well, isotopes are really the same element, but they have different masses. And this was one of those things, if you remember, with Dalton's atomic theory that we talked about, that was not correct. And that is really the existence of isotopes. Now, in order for them to be the same element, as we just talked about, they have to have the same number of what? Protons, right? So really what is different in terms of isotopes is typically the number of neutrons. So because they have different numbers of neutrons, they have different masses. And for example, hydrogen has 1 proton, no neutrons. Deuterium, which is heavy hydrogen sometimes referred to, has 1 proton and 1 neutron. And which is like the radioactive version of hydrogen, has 1 proton and 2 neutrons. And there is a special way that we write sort of our isotope symbols here that includes the mass and the atomic number. We use the symbol, and on the top left, we put the mass number, and on the bottom left there, we put the atomic number. So if we were to write our symbols for each of those isotopes of hydrogen, we would start with hydrogen here, which has 1 proton. By the way, if you weren't sure what hydrogen's symbol is, you can go to the periodic table and look at number 1, right? And that is the atomic number, which is the number of protons. And that would tell you that it should be hydrogen. The atomic number should be on the bottom left there, which is 1. The mass number, which is on top, is 1 plus 0, which equals 1, which means 1 should go up on top. And that would be the symbol there for hydrogen. And obviously 1 minus 1 there, top number minus the bottom number gives you the number of neutrons. So in this case, it would be 0. Deuterium, again, even if you couldn't recognize that's hydrogen, when you see it has 1 proton, you could go to the periodic table and go, oh, that's still hydrogen. And that would be obviously 1 on the bottom left. In this case, it is 1 proton plus 1 neutron, which gives us 2 for the mass number. And lastly here for tritium, again, if you had this name and the protons and you're like, that doesn't sound like hydrogen, but again, it is 1 proton. So it would also be the symbol for hydrogen with the atomic number of 1. In this case, obviously 1 plus 2 would give us 3 for our mass number there. So this is hydrogen, that's deuterium, and that would be tritium. Yeah. Any questions on that? Even though they all 3 have different names, they all are basically hydrogen because they all have 1 proton. They do all have different masses as the protons, neutron, and 2 neutrons here. On that. So that's a very common way that sort of isotopes are written. Another common way that isotopes are written sometimes is like copper 64, for example. So Cu-64, this number would represent, what do you think? Atomic number or mass number? Well, we can simply answer that by going to the periodic table, and under copper, I guess above copper there, symbol, is what number? Copper is 29, which is actually the atomic number, right? So that's actually the atomic number, which means this number is actually the mass number. So sometimes isotopes are written like that, the symbol dash a number, and typically the number that comes after the dash is the mass number. And obviously you can go to the periodic table there and find the atomic number. Any questions on that there? All right, let's take a look here. All right, so for each of these, determine the number of protons, electrons, and neutrons there are. So take a minute or 2. And really the important part to answer this is the correct identifications of each of these numbers. So as we talked about before, on the bottom should be our atomic number. And that basically is our number of protons. Up on top should be our mass number, which is our protons plus our neutrons. So that means in this case, CO, which is cobalt, should have 27 protons. Does this have a charge? The answer is it does not. If it did have a charge, something would be written there. So since we do not see anything written there, we assume it is, which means if it has 27 protons, it should have how many electrons? Should have 27 as well to balance it out. And our neutron should be top number minus bottom number, which would be 60 minus 27, which looks like a 30, we're at 33 there. Any questions on any of those there? Next one is chlorine. Again, looking at the bottom left number, that is our atomic number, which you can find on the periodic table. That tells us it is 17 protons. And to balance that out would be 17 electrons, as there is no charge there. And our neutrons would again be our top number minus our bottom number, which would be 37 minus 17, which looks like a 20 for the number of neutrons. And lastly, U is uranium. They're bottom of the periodic table there. And that is 92 for the atomic number. That means it has 92 protons. It also then has 92 electrons because, again, there is no charge. And 238 minus 92 is a lot, like $1.46 maybe or something like that. 146 there gets you the number of neutrons that are present. Any questions on any of those there? Again, you can see mass number, atomic number, protons, electrons, and neutrons, all whole numbers. So keep that in mind as you do this. Very common mistake people make. All right, let's take a look at some more here. All right, Krypton atom has 48 neutrons. Write the symbol with the mass number and atomic number for that. Should be looking for our good friend Kr, which is Krypton. The other important information we can get from the periodic table is the number that comes above it, and I believe that is a 36. That 36 is the atomic number, which should go bottom left of the symbol. And that means our mass number would be 36 plus 48. That should go up there on top for an 84. And we should have a symbol that looks something like this guy right here. Any questions on that one there? All right. Nitrogen has 6 neutrons. So take a look at there and see what you come up with. Nitrogen is, if we look up there on the periodic table, as we saw earlier, our good friend 7, again being the atomic number, which is also the number of protons. So that is 7 plus 6, which would give us 13 in terms of our mass number, which should go top left, and our symbol should look something like this. Any questions on that one there? And lastly here, we're looking for iron. What is its symbol and how many protons, electrons, and neutrons it has? And it has a mass number here of 56. Fe and 26 there up on top. They gave us the mass number, which is 56, which should go top left. Obviously, our atomic number there on the bottom. And we should end up with a symbol that looks like this. That means here our iron has 26 protons, no charge. So also should have 26 negative electrons to balance it out. And our number of neutrons would be 56 minus 26. And that would get us 30, it looks like there for our neutrons. Any questions on mass number, atomic number, how to calculate protons, electrons, neutrons? All right. So what happens though if we did have something that had a charge? So let's say we'll just take our last one there, which is our 56, 26 iron. And let's say it had a +2 charge. So things that have charges are things that are known as ions. And there's really 2 types of ions. There are cations, which are positively charged, and there's anions, which are negatively charged. So in this particular case, this is a cation, is positively charged. The number of protons here would be 26, right? Still the atomic number. The number of electrons in this case would be how many? It would be 24 electrons in this case. 24 positives, right? And 24 negatives. I'm sorry, 26 positives and 24 negatives leaves you a +2 left over. That is where the charge comes from, is that +2 that's left over. By the way, in this particular case, the number of neutrons would still be 30 in this case, right? 56 minus 26. So in comparison between the iron with the +2 charge and the iron with no charge, the number of electrons change. And did we have more electrons or less electrons in the guy with the positive charge? Less. So in order to become positively charged in a cation, you typically will lose electrons. When you lose electrons, you have more protons. More protons mean more positive charge than negative charge. And that is how come you become positively charged. Question on that there. How about if we had our friend nitrogen here with a -3 charge? How many protons would this guy have? It is still going to be 7. How many electrons would it have? It would be 10 in this case. 10 negatives, 7 positives leaves us a -3 left over, which again is where the charge comes from. In comparison of our nitrogen with a negative charge and our neutral nitrogen here, the number of electrons, right? And that is how come you become negatively charged when you gain electrons. When you gain electrons, you become an anion because you have more negative electrons than positive protons, and you end up with an overall negative charge when it's done there. The only thing that changes when something gets a charge is the number of electrons. How come the number of protons don't change? Yeah, because if you change the protons, you just change the element, right? So in the case of nitrogen, if I change it to like, 9 or 10 protons, then it's no longer nitrogen in that particular case. So it's never the protons that can change, only the electrons and somebody gains a charge. Any questions on that there? All right. I think that's a good place to lay it up here or take a little break.